Hello everyone and welcome back to another episode of the Hidden Quantum Champions. Today we are talking about the girl's best friends, which is diamonds. And the company that we are looking at is called Diamondfab. If you are interested in how diamonds are interesting for quantum applications and what Diamondfab delivers to cater these interesting requests, then stay tuned for today's episode. And with that, let's hop right into it. So here we are on the website of Diamondfab. Unleash the power of diamonds. You see there is like some wafer processing in the background and some crystal patterns. And we will learn now what the company actually has to deliver. So it says Diamondfab, unleash the full potential of diamond as a semiconductor. Positioned at the forefront of semiconductor technology, Diamondfab pioneers the deployment of its groundbreaking diamond solution tailored for high-power, extreme condition electronics and quantum applications. Exploring further with diamond material from volume and weight saving to quantum applications, passing by resistance to high temperatures, radiation, and high voltages, diamond offers numerous advantages. So the idea is to use diamond in a context of a semiconductor, so for electronic devices, for quantum devices. And the points that they are pointing out here is that they are, let's say, very resistant at high temperatures. So diamonds are carbon crystals and they are, let's say, very rigid. They have a very strong binding to them. So that's why they are, let's say, as a crystal lattice, very stable and very temperature resistant, making them also very radiation resistant and, of course, useful for high voltages because of the wide energy band gap that you have. And then for quantum applications as well, and we will see in a second why this is the case. 5 advantages of diamond. Here are the different applications named again as well. So we've seen volume and weight savings for like logistics or generally mobility applications, resistance to high temperature for any type of high temperature environment, quantum applications, resistance to high voltage, so energy transmission, high voltage type of setups, and then resistance to radiation. Here we see some nuclear power plants, but I guess that also caters towards like space radiation and space applications. 10 points to know about diamonds as a semiconductor, everything to learn. We will see a little bit more about that later. And then as per usual, we have the press reviews and the typical links down here. The company is based in Grenoble in France. Let's go up again and quickly take a look at the technology. So what is the solution that they are actually offering as a Diamondfab? So tackling the challenges of the energy transition is the first one. So as we move toward electrification and hybridization of our transport system, and as innovations and appliances require ever more electrical energy to operate, there is an urgent need to opt for materials that deliver greater energy efficiency and higher power density. Then technology for performance, involved in several fields related to diamond semiconductors and their applications. Our company is an expert in the growth of epitaxial diamond layers and in the development of diamond electronics components. So taking a step back, what is their offering? They are active in creating those diamonds, so growing those diamonds epitaxially, so probably at a very high quality, in a very controlled way, in a scalable way that can be used similar to how it's being done for semiconductors already today. Then it says reduce impact from manufacture to use diamond, contributes to energy efficiency by increasing the efficiency of devices and thus reducing the energy loss. It will also reduce vehicle energy consumption by reducing the weight of onboard power electronics and cooling systems. So this is number 3. And then I thought it was 10. Maybe that was just in my mind. Okay, so this is the 3 points that they are making here. Then benefits and applications. So that's now probably a zoom into the applications that we've seen before listed. So volume and weight savings, diamond electronic components for lighter and more compact converters. The volume and weight of a power converter can be reduced by 80% by using active components made of diamond rather than silicon. This is made possible by the intrinsic properties of diamond which enable use less semiconductor material, you reduce or eliminate the need of a cooling system, and reduce the size of passive components. Then there's the high temperature aspect. Diamond components capable of operating in very high temperature environments. Diamond is a high temperature stable material whose electrical performance does not deteriorate at temperatures above 200 degrees Celsius, unlike all other semiconductor materials. Then there's the radiation resistance as well. So there's no need to harden the components. Diamond components can operate at radiation levels in excess of 1 mega gray, for example, in nuclear reactor monitoring or aerospace. This is what I mentioned before. So aerospace and probably low, what is it called? Low orbit satellites. There is the high voltage aspect, so diamond components capable of withstanding several thousand volts. The intrinsic properties of diamond and our expertise in doping enable blocking voltages for several thousand volts, reducing switching loss by 95%. Quick point on doping. So doping is when you introduce other atoms in your crystal. So let's think about the diamond. The diamond is a carbon atom crystal structure. And now you are adding into this selectively at a specific dose dopants. So other atoms, usually if you're looking at the nuclear, at the periodic table, these are, let's say, offside to the left and to the right of the actual material, so of the carbon. And by this you can create so-called N and P doped areas. And these are interesting, for example, for diodes, but you also use them to create transistors, which are the basic building blocks of today's computers. So you can basically employ the same type of logic, but on crystals, and of course on diamonds. And of course that requires a whole new set of fabrication methodology. That is what Diamondfab is experts in. Then quantum applications as a final one, and this is of course the interesting one for us because of its exceptional properties and its ability to contain nitrogen atoms. Diamond is the ideal candidate for quantum applications, requiring neither low temperature nor high vacuum. So this is these NV centers that we've talked about before. If you want to learn more about that, make sure to check out the other videos in the Hidden Quantum Champions playlist that you find on the YouTube channel if you are looking at the playlist side. The NV centers, they can be, for example, used to build spin how do we want to call it, like magnetic sensors by using the spin of these NV centers, and that is kind of interesting for sensors, but could also be some kind of qubit. And the interesting thing is that because of the fact that this lattice of the diamond, the atomic lattice is so stable, that the energy gap is so high, you are basically more or less protecting or like locking in your quantum system or isolating it so well from its environment that you don't really need to put it at cryogenic temperatures. It already works at room temperature, and you don't need a vacuum because basically your NV center is completely surrounded by the carbon atoms, by the diamond crystal structure. So you don't need a vacuum for that. Okay, so that's about this. Then all about diamonds as the third side on the technology offers. So 10 points of diamonds as a semiconductor. First one, it is composed out of carbon. That's what we've talked about before. The carbon atoms that make up diamond are arranged in a face-centered cubic, so FCC crystal structure with half of the tetrahedral sides occupied, which gives it many of its superior properties. Also superconducting at low temperature, so minus 269 degrees Celsius, thanks to our expertise in high doping. Diamondfab wafers can be used for superconducting applications. It is a material with a very wide band gap. Its band gap is 5.5 electron volts, 5 times greater than that of silicon, which is only 1.1 electron volts. So that's why you might not even want to call it a semiconductor, but maybe already an insulator because of this high band gap. But then, of course, you can tune it, you can dope it, and therefore you can probably also create some semiconductor properties with it. So the result is a very low number of intrinsic carriers at room temperature, also known as insulator. This property led to it being classified as an insulator from the time of its discovery until it was doped in the 1980s. So then by doping, you introduce new free carriers because of these atoms that are, let's say, besides the standard neutral level in there, and then you have additional electrons that can move around, or holes, so lack of electrons, that have a certain mobility within the crystal, and that's what makes it then a semiconductor. It is the hardest semiconductor. With a Young's modulus of 1000 GPa, diamond is by far the hardest semiconductor. And that's why you also see like diamond-coated cooking pans and so on nowadays with and diamond blades, saw blades, because it's such a strong and tough material. It can be made in the laboratory. Two techniques are used to synthesize it. So there's the HPHT, high pressure, high temperature, or the MPCVD, microwave plasma chemical vapor deposition, which we use at Diamondfab. So the MPCVD is the one that they use, and the chemical vapor deposition is something that is commonly already used in today's semiconductor industry. And this is now enhanced with plasma, which I guess is produced by microwave radiation, and can therefore be tuned very gradually. And then tuning all of these parameters, you can then grow those diamonds. It can become more or less conductive. Diamond can be doped p-type with boron, or n-type with nitrogen or phosphorus. At Diamondfab, we master boron and nitrogen doping. So they can P and N dope the material, which is the requirement that you need to build kind of semiconductor structures out of this. And this is it's not explained how this is done in detail here. So implantation doping is not effective. That's why Diamondfab, we do in situ doping. We incorporate the doping species during growth. Okay, that's explained now. So during this MPCVD, they kind of introduce probably some gas, some chemical vapor here, which is intrinsically doping the diamond as it grows. So then you can grow like layer stacks, p-doped, n-doped, p-doped, and then you can kind of etch probably down, and therefore create devices with this. What is this other doping method that is mentioned here? So implantation doping. Implantation doping is when you have, let's say, a pure crystal, a pure diamond, and then you put it in something like a particle accelerator, more or less, or an ion accelerator, and then you are taking, for example, these boron atoms, you are making them ions, so you're removing one of the electrons from the shell, and then you are putting them in an electric field, and then they get attracted because they have an electric charge suddenly, because one electron is missing. They have a positive charge, so if you put a negative charge somewhere, they get attracted. And that's how you accelerate them. And then doing so, you can actually shoot them on a target, like for example on a diamond, and then they get shot into the diamond. They penetrate the lattice, so they go somewhere into the diamond. So some of them get stuck inside the diamond. And then if you, for example, heat up the system again, they get incorporated into the lattice, and therefore then the diamond gets doped. But they say here that this is not what they are using, because they say it's not effective. Then it also says here it dissipates heat better than metals, so its thermal conductivity is around 2200 watts per millikelvin, 5 times greater than that of copper. And then finally, then the ninth point is an unparalleled breakdown field. The breakdown field of diamond is 10 megavolt per centimeter, is 30 times greater than that of silicon, enabling diamond diodes and transistors to withstand voltages of several thousand volts in the off state. What does that mean? So if you think about a diode only lets current go through in one direction. So a current always means there's some electric field that is existent, that makes electrons move. And if you now apply, for example, in the reverse direction, the voltage, then no current is flowing, right? You create some charge barrier within that diode. Now, if you crank up the voltage further, at some point, this kind of barrier will break down, and then you will have some type of avalanche effect, and suddenly there will be a current flowing through your diode again. And this is, I think, related to this breakdown field that they are talking here, which is much higher, so 30 times higher in a diamond than in a classical semiconductor. So you can build diodes with that are withstanding thousands of volts, right? That's what it says here in the off state. So you can use that for some type of high voltage applications where silicon diodes might not be sufficient. And I think that is also, again, related to this bigger band gap that you have within the crystal. And then finally it says higher current thanks to fast charge carriers. So holes and electrons in diamonds have mobilities of 2000 centimeters squared per volt second and 1000 centimeters squared per volt second respectively, which limits Joule effect loss when diamond diodes and transistors are in the on state. What does this mean? So the electron mobility is more or less how well the electrons can move within the lattice. Let's say how smooth the electronic field in the lattice is, so that the local electronic field in the lattice is, so that the electrons can move without kind of bumping into the crystal. That's, let's say, a very high level explanation. Of course, there's much more to it when you look at it on a microscopic / quantum level. But imagine it like this, and there are so-called high electron mobility transistors, HEMTs, which you are, for example, using in RF technology, in radio frequency technology, because you need to be able to kind of switch things very fast. And here in this specific case, it says that diamond has also very high mobility, so the electrons can move very well within the diamond, and that's another argument to look into those for certain applications. With that said, as per usual, let's also quickly take a look into the company profile. So what is Diamondfab actually, who's behind the company? So the power of diamond, it says here. The company Diamondfab is a deep tech startup based in Grenoble as a spin-off of the Institut Niel CNRS. Its technology is based on 30 years of R&D into the growth of high-quality synthetic diamonds for demanding electronic applications. And I guess here you see the founders. So since its creation in 2019, Diamondfab's ambition is to bring this know-how to industrial scale to help solve major societal problems: energy efficiency, electric mobility, green hydrogen production, reducing the carbon footprint, and recycling nuclear waste are all areas in which our technology can make significant improvements. Diamondfab has been housed at the Institut Niel CNRS since 2019. And here you see the team. So this is, I think, that's the head office. Then you see the operation team here as well. Quite a lot of people. There is a board as well with different, which consists out of people from venture capital, but also, account manager, investment. So you see that there is like the investment board, and there's also an advisory board with strategic advisors and scientific advisory as part of this company as well. An application-oriented approach, a technological approach combining diamond growth and applications via the development of electronic components, has enabled us to acquire unique expertise and control over the quality and properties of epitaxial diamond layers. A Diamondfab strategy is based on collaboration. Our partners, future customers, and our suppliers provide unique know-how and essential contribution to the development of cutting-edge applications. And here we see some pictures, I guess, from the lab. This is probably the growth apparatus that they are using, and that's what like the chips with the diamonds are looking like. So you see it here in the tweezer. It's a very tiny object. It's with microscopic structure on it, like you know it from the semiconductor space. Here are some supporters of the company. So you see companies like, for example, You see the Quantum Business Network, for example, in here, but you also see that the European Union is part of this. Of course, the institute that was mentioned before. There's also the region of Grenoble, which is involved into that, and others. With that, I think we are already at the end of today's review. For me, clearly one of the hidden champions in this space, so one of the providers of, let's say, the technology stack. Diamonds, not only interesting for quantum technology, like everything that is on the optical side of quantum, and then trying to combine the semiconductor space and the let's say new material space, as in quantum, diamonds, optical accessibility, so combining those. But then on the other hand, also some use for, let's say, classical electronics, for semiconductor oriented new use cases. So for me, clearly one of the very interesting ones to observe. I hope the same for you, and I hope you like this video. If you don't want to miss out on the next one, as always, make sure to subscribe to this channel and always stay hydrated, and I will see you in the next one. Bye bye.